Hi students, this video is on acids and bases. So in this video we're going to talk about first what an acid is and then what is a base, and we'll compare the two of them and also look at their characteristics and see how they differ just with some of their general characteristics that aren't just chemical, but then we'll really look at the chemical characteristics and see what the difference is really between acid and base chemistry. And then we'll look at this idea of pH and see really what does pH measure. Okay, well first looking at an acid. So an acid is something that would be textbook defined as something donating a proton, or what we call a hydrogen ion. And that would be donated to an aqueous solution. So a couple new terms there that we want to go over. The aqueous solution idea, we've actually talked about this before. This is where water is the solvent. That means aqueous, aqua, right? The word aqua means water, and so that's a helpful way to remember. Aqueous means just dissolved in water. But the proton idea, this is kind of interesting. You remember back when we talked about ions that a proton, in this case, a hydrogen ion, if I look at the periodic table and I look at hydrogen, its number is 1. It's the first element on the periodic table. And if you remember, the number goes with the number of protons that that thing has. So if the element has 1 proton in the middle, that means it has 1 electron on the outside. And if that electron on the outside is lost, that can happen, right? The electron gets lost and now we have an ion formed. That's how an ion happens. So the electron gets lost. Well, now I have basically just a proton all on its lonesome. 1 little proton. Now, that would be the definition of a hydrogen ion, also called H+, and that's what we're talking about. So a hydrogen ion in solution, when it's doing that, it will turn litmus paper red, like we see here. It will have a pH value that's on this end of the spectrum, 0 to 7. So more hydrogen ions makes for an acid, anywhere from 0 to 7 or 6.9 really, because 7 is neutral. And then also conducts electrical current. This is kind of an interesting thing. If you put a wire and try to run electricity through water, it won't conduct electricity if they don't have any dissolved ions in there. But because you're putting something that ionizes and turns into hydrogen ions and whatever else that will ionize, we'll talk about it with an example here in just a moment, that will actually conduct electricity. So there's that aspect, and it also has a sour taste. I wouldn't recommend tasting, any acids in the lab, but lemons, vinegar, other types of acids that we do taste that are in foods, those definitely taste sour, and we can say that actually for the rest of the acids, even that are in the lab. Additionally, just wanted to show you how this kind of breaks up chemically. So in this example, this is hydrochloric acid, HCl, and hydrochloric acid, when it gets dissolved in solution, dissolved in water, it breaks up into hydrogen and it breaks up into chlorine. So this hydrogen goes off over here, this chlorine goes over here, they part ways, and as they dissolve into water. The chlorine kind of makes sense, right? The chlorine is dissolved in there. It's got that negative. But what is this about? Well, we're going to talk a bit more about where that comes from. This is called a hydronium ion. And a hydronium ion basically is the addition of a proton to the water molecule. We'll talk a bit more about that. But that is basically kind of a shorthand for the proton in this case. It's just after another reaction has taken place. So when you see that, think acid. And that's actually being shown here as a kind of a space-filling molecular view here. So this is the H3O+, and then here's the chlorine over here. So that's showing how HCl dissolves into water and how acids dissolve in water. Let's look at bases. What is a base? Well, a base is a substance that doesn't release a proton, it releases this thing. This is called a hydroxide ion. So a hydroxide ion is basically kind of like one proton taken away, or one hydrogen taken away from water. Instead of H2O, it's just H and O, or OH is the way that we write that. So a substance that releases an OH ion to aqueous solutions is what a base is defined as. It will turn litmus paper blue. It has a pH value, not over here, but it has a pH value over here at 7.1 up to 14. And some examples would be like antacid tablets. Those are bases. And a lot of other cleaning solutions and products often are bases as well. They also conduct electrical current just like acids because they ionize just like acids. And they have a bitter taste to them versus having a sour taste. So let's look again at how the base breaks up, like we did at the molecular view, like we did with the acid. So sodium hydroxide is our example we're going to look at here. And sodium peels off and ionizes on its own. And then hydroxide, rather than breaking up in multiple pieces, breaks up as what's called a polyatomic ion. And this polyatomic ion, or hydroxide in this case, is floating around on its own. And you can kind of see that molecular view over here. Now, don't get confused when you see this. This doesn't mean hydrogen ion. This is just a shorthand for a positive, a cation, a positive ion floating around in solution. In this case, it's sodium. There are other electrons in there and lots of protons, so that's not hydrogen ion. But you are looking at the main player here for bases, and that's the hydroxide ion. So hydroxide is what defines a base. Well, what about neutral solutions? Before we move on to the chemistry of acids and bases, what about neutral solution? Well, the thing that defines a neutral solution is that it doesn't do either of these things. It does not contain the H plus or OH ion when it's dissolved in solution. If it does that, then it's either an acid or a base. So one example here would be salt. So NaCl. In this case, or actually this is NaF, the picture I got offline, but NaCl would look the exact same when drawn this way. So salt or sodium fluoride, whatever it is, dissolved in solution. There are no hydrogen ions in this solution. It's just sodium and fluorine. So because there's no hydrogen ion, it's not an acid. Because there's no hydroxide ion, it's not a base. So compared to this one over here, which has a hydroxide ion, these are examples of acids and bases. So you're looking for the hydroxide ion. Obviously, other ions can be in solution, but if you don't see hydrogen or hydroxide, then you're not looking at acid or base. Some solutions contain no ions whatsoever. So like sugar doesn't break up into ions, doesn't ionize, but it does dissolve. So sugar can be an example of something that just doesn't ionize at all, but clearly that's also not going to be an acid. So let's look at this idea of water and how water interacts with acids, and really how can we understand this H3O plus thing and the OH minus thing. Well, first off, between water's hydrogen and oxygen molecules, not within a molecule, not here, but between the two adjacent molecules, two that are next to each other, there's this bond called the hydrogen bond. And you might remember that one from intermolecular forces when we talked about those. Now, the hydrogen bond is a very strong bond relatively for intermolecular forces. Not as strong as like an actual covalent bond or ionic bond, but it is a strong bond and can explain why water has cohesive properties, sticks together, why water has surface tension, why water can form ice crystals in the way that it does. Hydrogen bonding is really important. But what can happen with a hydrogen bond is actually there's a rare occasion where the attraction here can actually peel off the hydrogen from one molecule of water to the other, and you end up with H3O+. this happens, and OH minus obviously over here. This happens, but it's extremely rare. So it's not often that you have this occurring. The odds are 1 in 10 million, okay? That is like almost never. If you think about like, your odds of winning the lottery, it's something like that. But because there's so many trillions and trillions and trillions and trillions, and we could go on, of molecules in even just a couple drops of water, this is actually fairly common, because 1 in 10 million, when you have so many trillions of molecules floating around, is actually not a super uncommon thing to find in there. It's just still relatively rare comparatively to how many molecules are in there. So here's what happens though, when, though this happens at a rare number, if you add an acid to water, well, I've started to add, so this would be adding an acid, I've started adding more hydrogen ions to the solution. And what is that one going to go do? Well, it couldn't go over and add itself to the hydronium, but it could move itself over and add itself to the hydroxide. And when it does this, it creates just a regular water molecule. Okay, so that regular water molecule was created by the addition of some hydrogen that came from an acid. And of course, we're going to add more in there, and there's more stuff floating around. So here's some more acid that got added. Where are those going to go? Well, in this case, these ones could go get added onto other water molecules. Now, of course, there's plenty more water molecules than we have acid added. So these H3O plus molecules that have been created will be in abundance, but there won't be so many that there's not any regular water floating around anymore. But the stronger the acid, the more of these there are. And that is what pH measures, okay? So pH is a measurement of how many of those there are. So here's the big idea surrounding acids. Acids have H+, at least as an ion that forms. And then that ion forms the hydronium as a product, basically. As soon as that hydrogen ion goes in solution with water, it forms H3O+. And then that happens just way more often in acidic solutions than it does in basic solutions. So we look at the level of this ion, and the concentration or the level of that measured, either sometimes just reported as hydrogen ion concentration or as hydronium ion concentration. That is what pH is. Okay, so this equation actually kind of goes backwards and forwards, and water can form this hydronium and hydroxide, or it can form it can go back the other way and form water. So acids do that, but bases actually form hydroxide. So in this case, it's going to go this direction, where hydroxide is added by the base, and that's going to react with any free H3O plus that's out there, or hydrogen ions that are floating around. And that will just make lots of water and basically take away the concentration of hydrogen ion. And we said a second ago that pH is measured by the level of hydrogen ion that's out there. So bases basically just bring the hydrogen ion concentration down a ton. And that's actually how you measure the pH, is how much hydrogen ion concentration there is. And I'll help you understand that in just a second. So solutions with more OH will be less acidic because the OH will convert all that hydrogen ion to water. So pH is essentially the power of hydrogen ion that's in the solution, the amount of it. So our equation, it's going to look a little daunting. Right now, we're not going to process through how to solve for this. It's actually pretty simple, but it's the negative log of hydrogen ion concentration in solution. And essentially what that equation does is it takes a really tiny number and turns it into an integer, into a whole number. And that's basically what happens here. And you can just see the correlation between these, right? The negative 11 becomes 11. The negative 9 becomes 9. The negative 7 becomes 7. And basically what you're seeing is these concentrations, as they're actually getting greater, this is a small number, it's a super small amount of hydrogen ion, and this is a relatively large amount of hydrogen ion. That these numbers translate to an integer or a whole number. And so as it goes down in number, you actually get more acid in your profile. And so we think about it this way: higher concentrations of hydrogen ion, or H3O+, you can measure either, are smaller numbers on the pH scale. Lower concentrations are larger numbers on the pH scale. So that's pH and acids and bases and how they look molecularly and chemically. I hope that was helpful.